This is a download from the BBC.
Welcome to The Forum, the BBC World Service programme where our experts share their knowledge to help you understand what matters. Hello, I'm Bridget Kendall. I expect that you're listening to this programme on a radio, lap or desktop or a mobile phone. Now imagine a world where the digital technology which underpins all these modern appliances suddenly disappears. Well, it would be a much quieter place for starters. The integrated circuit, better known as the Syllicon chip, has unleashed change which has been compared to the Industrial Revolution, allowing the creation of the modern computer and making the digital age possible. Today, there are far more chips than people, millions and millions of them, driving our mobile phones, laptops, television sets and printers, in our cars, trains and planes. Silicon chips are found in almost all electronics. So can you imagine a world without them? I know, I certainly can't. It's 45 years since the commercial introduction of the first microcomputer chipset, which evolved into the modern microprocessor, changing computers from tools for scientists into the engines which power today's electronic consumer appliances. So how did the Silicon chip evolve? And where might this revolution be heading next? I'm joined by four distinguished computer and internet pioneers who helped spearhead some of the most important inventions of the computer age. Vinod Dham was at the forefront of the chip revolution in America's Silicon Valley in the 1970s. He invented the first Pentium microprocessor and went on to become vice president of the world's largest chip maker, Intel. His early work in this field earned him the nickname, the father of the Pentium chip. Sophie Wilson's computer designs were used to build the Acorn microcomputer, the first computer sold by the British technology company Acorn Computers. She went on to lead the development of the ARM microprocessor, found now in over half the world's consumer electronics, and the FirePath processor, which supports broadband infrastructure worldwide. David Laws is another veteran of Silicon Valley, where he's spent his career designing and developing chips. Now he's a technology historian and a curator of the Computer History Museum in California. And Dame Wendy Hall is a professor of computer science at the University of Southampton here in the UK. She's made a significant contribution to our understanding of the interactions between humans and large networks of computers, such as the internet. She worked alongside Sir Tim Berners-Lee on an early version of the World Wide Web. Welcome to you all, and I want to start with you, David Laws. Can you give us briefly a definition of what we mean by a silicon chip and how they work?
Silicon devices actually go back much further than most people remember. Crystal radios, in many cases, relied on silicon chips, but silicon semiconductor devices really didn't come into their own until after the invention of the first transistor in 1947 that was germanium. Silicon as a superior material followed pretty quickly after that, and between 1957 and 1960 scientists figure out how to put lots of transistors on a single chip and interconnect them all together into a device we call an integrated circuit.
We should just say that a transistor is the device that regulates voltage flow and acts as a switch or gate for electronic signals. Transistors consist of 3 layers of a semiconductor material, each capable of carrying a current. The first transistor was developed by research scientists John Bardeen and Walter Brattain at Bell Laboratories in the US in 1947. They worked in a group led by the physicist William Shockley, and all 3 went on to win the Nobel Prize for Physics. Here's Shockley speaking on the 25th anniversary of their invention.
What we tried to make was a thin layer of semiconductor. These already did exist in the laboratory. And then we tried to change the conductivity of that layer by bringing in more electrons by charging this layer electrically. And we charged it by putting a plate of metal near it and putting a voltage on the metal plate, which would then act like one plate of a capacitor and would then charge the layer of semiconductor.
That was one of the inventors of the transistor, Professor William Shockley. So how exactly does a transistor work?
The computer on a chip has thousands and thousands of tiny switches, and just like your light switch at home, each single transistor switch can be only on or off. Under the electron microscope, you can watch the switches operating on the chip. At full speed, each one can operate millions of times a second. And the way computers think is like this too. They deal in simple alternatives. Yes or no, do this or do that.
That clip from 1980 came from the BBC archive. It was in 1958 that the American Jack Kilby, then a junior engineer at Texas Instruments, had the idea of constructing a single device with all the needed parts that could be made of silicon and soldering it to a circuit board. He understood that if he could eliminate the wires, he could squeeze more parts into a smaller space, thus solving the obstacle of manufacturing complex transistor circuits. He'd invented the integrated circuit, or silicon chip. David.
They're made by extremely complex processes of evaporation, deposition, high treatment, and slicing and dicing chips to put them in packages. But today, integrated circuits have evolved from just 2 or 3 transistors on a chip to daily manufacturers around the world are putting more than 1 billion transistors on chips that are being shipped in modern computers and other devices.
Wow. Finn.
I started my career at the age of 21 in 1971 in India and accidentally started working in the only silicon semiconductor company that the country had, working with 1-inch diameter wafers. You know, you can't even believe that's just the size of a quarter.
When you say wafer, what does it mean, the wafer?
If you were to open a computer or open any of your smartphones or anything, what you will see is a rectangular or a square device, which you can't see anything inside. It's just a solid black color thing embedded on top of the motherboard or the card that carries all the rest of electronics. But if you open it and look inside, there will be a chip. You will see actual piece of a physical piece of silicon, which may have 20, 30, 40, 50, 60 layers of different types of materials deposited on it. There's about 250 steps of processes that take place in order to make those silicon chips come alive. But those chips cannot be produced by themselves as one each. It'll be too expensive and impossible to do that. What's done is, from a crystal of silicon, a pure crystal, we slice it off. The crystal is grown in a tubular form. Just imagine a cylinder. And then you just slice off that cylinder into thin slices of salami, like you will see the salami itself. And that each of those slices of salami is like a wafer. And that's a pure silicon. And now in that silicon, we diffuse different impurities, dopants, to create these transistors, which are basically on and off switches that allow us to do the computing that we want to do.
David.
Just a sense here, Bridget, of the dramatic changes. If you think those first integrated circuits built in 1960, 61, and there's a unit of measure used, what's the smallest line width you produce? In those days, it was about 10 to 20 microns wide, and you think of a human hair as being 85 to 100 microns will give you a sense of scale. Over the years, the lines were scaled smaller and smaller and smaller, and today the lines on these billion transistor chips are in the order of 10 to 20 nanometers. A nanometer will be a billionth of a meter. If you think of that size relative to a carbon atom, is about 0.3 nanometers in dimension. You can see how tiny the lines are which are being produced today on silicon chips, and that's why we can cram so much more onto them.
Vin, what are your early memories of the early chip-producing factories? What were conditions like there?
I was one of the 10 or 12 people who helped set up entire diffusion, epitaxy, photolithography, etching, metallization, all the steps that are required to complete a transistor. And we were building those in-house in clean room conditions with deionized water, with all these hundreds of things you have to be careful about to build those chips. And that's where you had to wear coats and you had to wear caps on your hair so that the particles that you could breathe on the wafer could destroy. They're so small in dimension, they could destroy the functioning of the wafer itself. So you have to be very careful about how you are handling those things. So that's the era that I was involved in actually building chips.
And David, did it start out with blue-collar workers crouched over benches?
Well, the first transistors, of course, were built by very well-trained scientists. As the technology became better understood, it was turned into relatively high-volume manufacturing, but still every step had to be hand-done. each transistor was individually made, individually wired into a package, and individually tested. Until Herney's planar process came along. Instead of making transistors one at a time on a little pellet of germanium or silicon, you could put hundreds of transistors on a single round piece of silicon. Then they would be tested while on the wafer. Then they would be cut up into individual little slices and put into packages which would be hand-wired using bonding, welding methods, using little gold wires. And indeed, there would be vast numbers of individual operators, most of them female, who would sit down all day long assembling these little transistors, peering through microscopes.
Let's go back to 1967 now to get a sense of what it was like inside one of the production plants in the UK.
Now the diffusion process is finished, and this is the complete slice with about 600 individual circuits on it. The slices are scribed with a diamond-tipped needle to separate the circuits. The needle scratches a thin line in the oxide layer on the slice. The girl operator has to position the needle in the gap between the circuits, which is only 0.02 of an inch wide, and she has to cut about 50 lines on each slice. The whole operation takes up to 10 minutes. Then the slice is easily broken along the scratches to give all the individual circuits.
As the devices became smaller and smaller and more complex, they became too small to be handled individually, and automated methods were developed for doing not just the processing of the wafers, but for testing them and for cutting them up and putting them into packages and having basically little robot welders attaching all the wires to them, which is what happens today. From just very large rooms with people wearing blue coats and hats, now there are very, very few people in a silicon factory, which probably is the size of a large city block.
When the silicon chip revolution really got going, it seemed to centre on the San Francisco Bay Area. David, that's where you were working. It became the focus of activity for the early chip-producing companies, didn't it, known as Silicon Valley?
Shockley decided that he wanted to start his own company, and Shockley's mother lived in Palo Alto, so he decided to set his company up there. So you have this confluence of an infrastructure of technology, of risk-taking entrepreneurs, and some specific knowledge in the manufacture of semiconductors, which converged in the center of the area that's now called Silicon Valley. Shockley started his company. He was a brilliant, brilliant mind, but he was just a terrible manager and egotist, and 8 of his most brilliant young engineers that became known in the valley as the Traitorous 8 set out on their own to start their own company where they felt they could control their destiny. They raised money from East Coast financier Sherman Fairchild. They started Fairchild Semiconductor. They came up with a better transistor, and their timing was absolutely perfect. A month after they started their company, Sputnik went up into space and shocked the U.S. into the need to get into more advanced technologies, and Fairchild thrived and did very well early on and would have been another successful company except for one of the engineers, Jean Heny, a Swiss national, came up with a better way of making transistors. He called it the planar process. The planar technique allowed him to make transistors that were more reliable, faster, but most important, it transferred the manufacture of semiconductor manufacturing from a handcrafted operation to a high-volume automated process. Herney's boss, Robert Noyce, who later became one of the founders of Intel, looked at Herney's process and figured out that, wow, I can use this to interconnect multiple transistors on a chip. And lo and behold, Noyce came up with a practical way of making integrated circuits. A third member of the team, Gordon Moore, came up with an idea. He recognized that the number of transistors on a chip was increasing quite dramatically with time. He drew a line through 5 points on a curve marking each year's increasing complexity and said, wow, in 10 years' time, we'll be able to put 65 or 70,000 transistors on a chip. This became known as Moore's Law, and everybody started to think, well, if Gordon says it can be done, it will be done. And people found ways of making more and more complex chips. Within 20 years, over 120 companies had spun out of Fairchild, and there was this incredible infrastructure which enabled the industry to continue to grow and thrive.
As a computer historian, David, sketch us a quick picture of what early computers looked like before the invention of the silicon chip.
Computers go way back to mechanical devices, such as the Babbage machine, the Victorian computer that was built in London. In the 20s and 30s, people started building computers using relays and other mechanical methods of calculating. The first electronic computers came about during the Second World War, with the Colossus developed at Bletchley Park for decoding ciphers, and then quickly followed by the ENIAC machines built for calculating missile trajectories. But all these machines used as the fundamental component a vacuum tube, or radio valve as they're called in England, to perform the switching connections. By the time transistors came along, it made much smaller computers possible, faster, cheaper, and using less power. And during the 1950s and early 1960s, these were still very large machines devoted to scientific and engineering calculations, but it was the advent of the integrated circuit in the early 1960s which made machines smaller, more capable, lower power, and available to individuals. First came minicomputers, then became microcomputers, made possible by the development of the microprocessor device by Intel and others. And ever since then, computers have become smaller, more ubiquitous, such that every day we're surrounded by tens, if not hundreds, of computers that help us live our lives.
Wendy Hall, can you remember the world before mini-computers and microcomputers?
Not much. I did do some programming, Fortran program, when I was at university with the big mainframe we had in those days, but I was a pure mathematician. I wasn't very interested in that. I got interested when the personal computers emerged in the 1980s, particularly the BBC Micro, which of course was an Acorn machine.
Sophie, that's where you come into the story. Pick it up for us, these early personal computers. What were they able to do? How did they change the way people could use computers?
My first experience was reading about them in magazines, and then I joined a special interest group for microprocessors, the Cambridge University Microprocessor Society, where there were like-minded individuals, people who just talked about microprocessors, and we bought the things, and we were able to make our own computers entirely from scratch. And then obviously we went on to make computers for other people as well.
Vinod Dham, what about your early involvement? Because you got involved, I guess, as a young graduate in the 1970s when you moved from India to the United States. What were you able to work with in those early years?
We also had on campus a big IBM mainframes that we used to do a batch processing with. So it was completely different era than the personal computer era. It began to change actually only in the 80s in a mainstream manner. During the late 70s, we were using computers mostly for research. We were creating research in flash technology, which is what you use for storing photographs today. So we were using electronic devices to store information and recall it. That's where I was using computers to do the research for those devices, not actually to build those devices.
I just wanted to come back to the world, the culture in the heyday, the gold rush days of Silicon Valley, where you were never quite sure whether you could cross the next threshold, but somehow it seemed possible, but it was incredibly intense and very long hours. And I just wanted to ask you, Sophie, who were on the other side of the Atlantic in the United Kingdom, also in your pioneering work in the 1980s, pushing the boundaries, trying to find out what you could do. Was this a similar culture that you had in the United Kingdom, the sort of excitement and uncertainty, but also constantly pushing yourself?
We started work with microprocessors during the 70s when I went to university. I was programming mainframe computers, big IBMs with punch cards and that sort of thing, and then going home and reading about microprocessors and how something could be more personal. So in the 70s, I built my own home computer. Herman Hauser, who formed Acorn Computers, cherry-picked people out of the Cambridge University Microprocessor Society to help him realise his ambitions of getting involved with the Syllicon chip. He'd got very excited at early BBC TV programmes about the coming microprocessors, and in forming a business he knew that's where he wanted to be, so he cherry-picked people to work on things for him.
Is it true also, Sophie, that in your part in the development of the personal computer, the BBC computer and then the Acorn computer, that actually you were under pressure to produce a prototype in under a week and managed to do that?
Given that Herman had started up a thing that was a consultancy at first, it became interesting, the computers that we were using to do the consultancy, and he began to wonder if they could be sold. So he set up a commercial arm and we started selling the kit that we developed to run the consultancy. So Acorn System 1 and so on all sort of happened. And those were the times when we were working 7 days a week, 12 hours a day, without cease. You'd go home to sleep. Everything at the time was totally different. There was no standard. The IBM personal computer was in the future. So the BBC wanted to commission a microcomputer design to its own specifications. So it worked for quite a long time with a company and got nowhere. So Chris Curry, another of the founders of Acorn, approached the BBC to say, well, come and have a look at our working prototype of our next generation computer, which far exceeds those specifications. And we had no such computer. So Herman played a trick on Steve Ferber and myself. He rang up each of us independently. We still don't know which one he rang up first, but the conversation went something like this. Hello, Steve. We need to build a prototype of the Proton computer that you've been thinking about for a while. And of course, at the time, we had no prototype. We had nothing really. It was castles in the air at the time. So we had thoughts. We had no circuit diagram. We had no components or anything. Steve naturally said, well, that's impossible. Then Herman played his trump card. He said, well, I've talked to Sophie and she says it is possible. And Steve reluctantly agreed. OK, if I said it was possible, come along and give it a go. And of course, Herman had said exactly the same thing in reverse. Steve said it was possible. I thought it wasn't. So we turned up on Monday, determined to give it a go. So between Monday and Friday, we built the BBC microcomputer prototype from scratch. Before we drew the circuit diagram, we ordered all the components because we had very exotic parts for those days to put into it. We had 4 kilobyte RAMs, 16K by 4 DRAMs to put into it. We found all these exotic things and got them ordered. Some of them were so exotic they're hand carried by representatives into the building, and we worked away.
And you managed to do it. It's amazing, these stories of this early pioneering work and the dramas that everyone went through. Wendy, you were also here in the UK. How far do you think that people in this country were aware of everything that was going on the other side of the world in Silicon Valley?
Well, of course, the specialists were very aware, and here at Southampton, we've been working in this field for a long time, and the researchers and people in the industry were very aware. But the public weren't. I don't think the public were aware at all until the personal computers began to hit the market. And then it was a very small market until the wave that hit once the web was came into being.
We've already heard how the Silicon chip was invented and how its early designers went on to form some of the most powerful companies in the world. But let's look now at how far we've progressed since those early years. Sophie, we've talked about this in passing, but just for a recap, give us an idea of the rate of growth. How much information can now be stored on a microprocessor? I've
been working with microprocessors for 40 years. During that time, we've had many, many generations of Moore's Law. I started on 3-micron designs. That's what ARM was built on. And we're now on 28 nanometer, 14 nanometer, and shortly we'll see the first 10 nanometer chips in production. That means that equivalent functionality is about 70,000 times smaller in area, or alternatively we can have machines that are roughly 10,000 times more capable than where I started. And most of that comes all through having smaller transistors. The smaller transistors run faster, so about 1,000-fold of that increased capability comes just from running faster. And the other 10-fold comes from refinements in microarchitecture, how a microprocessor is built. It's mind-boggling numbers to think how these things have grown or increased or, in fact, diminished exponentially. Wendy, though, this is a story not just about how much information can be stored on smaller and smaller chips. It is also about the costs, isn't it? The cost of production. Will the cost of devices, such as mobile phones and laptops, keep rising as their memories become more and more powerful, or will it work the other way around?
As things become smarter, the cost goes up initially, and then it will come down as the next wave kicks in. So they're always going to charge a lot for the new technology because it's cost a lot to develop it. When it becomes standard, ubiquitous, it'll be cheaper.
Sophie?
The numbers are what drives it. So one company, ARM, has supplied technology to make 90 billion chips to date. So that's incredible numbers. The silicon industry itself is about $300 billion per year in size. That's how it can afford such massive developments in physics, chemistry, optics, etc., that makes the printing of the chips possible. But most of that comes from mass production. To make Internet of Things devices or anything small and cheap, you have to make them in volume. You can't make them personal.
Just so we understand, Wendy, the Internet of Things, exactly what we mean by that.
It means lots of small devices talking to each other or to bigger computers via the internet. This is a wave that's about to hit billions and billions and billions of devices that will become part of the internet in the future.
So the big question that they're all dancing around is whether Moore's law, this idea that every 2 years the number of transistors on a particular area of silicon could double, that this would be the driving force that would keep making things smaller and faster and possibly cheaper, whether we're reaching the limit. Vin, what do you think? Can we go any smaller, or is there a natural limit?
We are reaching two limits. One is clearly the atomic limit, that is the thickness of oxide and the dimensions of the atom itself, the silicon atom. They start interfering with each other and therefore creating a very clear state of 1 or 0, which is what you need to define to have an on or off state that defines the basic computing, is much, much harder. But I think even more than that is the cost of computing is also creating these fabs or machines that can allow you to define those dimensions is becoming extremely prohibitive. And so very few companies can afford to even invest the kind of money that's required to get down to even the levels that I'm talking about.
Is there a possibility that we could move beyond the silicon chip then? You talked about the silicon atom. Look at another material which would allow one to go further, cross another threshold.
There has been actually a lot of work being done for more than a decade now on carbon nanotubes and new types of materials that will take us beyond silicon and continue this exponential growth of Moore's law well into the future. And some of them have had good successes in the R&D environment, but none of them have yet broken out into what I call high volume manufacturing phase. That is, if you create standards, then you can create volume. If you have no standards, then each person is doing something different. You never get the volume, and therefore you never get that scale that allows you to create the cost and efficiency and the markets that are required.
You need to have mass production to make it cost effective.
Exactly. And we don't have any of these new technologies yet hit that threshold where we can produce them in mass, and therefore we are not able to bring them out yet into the markets.
David, what's your view on this as a technology historian with a long view?
If you think about it, the transistor is the most fabricated artifact that humans have ever made. There are now more transistors made every year than there are grains of sand on the beaches of the world. That's not going to stop overnight. Somehow we're going to figure out a way to keep this moving forward. Molecular computing and many other approaches have been discussed and are being worked on, but silicon has been such an incredibly powerful material that it's always been easier to continue down the path of ever smaller silicon devices than going in other directions until now.
What's your perspective, Wendy? Because you were talking about the Internet of Things as a wave that could be about to hit everybody because of this way that machines could talk to machines. But it is interesting, isn't it, that when you get down to the basics of computing, you have to get down to the actual nuts and bolts of what it's made of, these tiny grains, these little silicon chips. Do you think that the physical properties, as we've been discussing here, that maybe we could be reaching the natural limit, that this could stop what, in theory, you could imagine being the next generation of digital development, in other words, the Internet of Things?
It's been easier to push on the silicon than it has been to bring in another type of material, or even look towards maybe quantum computing down the line, which is another way of doing the computing, another way of doing the software, to bring us the increases. You mustn't think the Internet of Things, the things are not they're not going to be computers. They will do very simple jobs jobs. It's the network effect that will make it all integrated together, that will make things different. The internet enables the computers to talk to each other now, and that has been a major breakthrough in terms of giving the public access to these types of devices.
Sophie, you were talking about the real world of the economic realities of this. You think that's currently the threshold that's difficult to counter?
90 billion chips is an awful lot. Where are they all? A huge percentage of those chips are providing us with communications. The broadband that comes to your house on a cable, the Wi-Fi that's in your house, the Bluetooth that you use to connect your headphones, etc. All those communication standards are built and run by microprocessors on silicon chips. So a lot of those microprocessors are deployed running communication systems. And the Internet of Things needs communication systems. It needs microprocessors to run those things. It doesn't need particularly aggressive microprocessors. They're doing a simple job, but there'll be a large number of microprocessors.
We've been talking about where all this technology may go next, given how fast it's gone in the last 40 years. But another whole area of questions about this are the pros and cons of what this industry has done to us as social beings and also to the world we live in. And one impact that people talk about is the environmental impact of the chip industry, and particularly what happens to the waste from old appliances. David, what's your view on the impact of the production of so many chips? You said more than grains of sand. What do you think about this?
Well, there certainly was a real serious lack of understanding in Silicon Valley in the early days of building chips as just what the pollutants and what the other things involved in production could cause on the environment. But I think today it is so well understood, and the cost of cleanups is so expensive that massive amounts of money have made, in many ways, it one of the cleanest industries in the world. There are chemicals that must be handled carefully after the manufacturing is completed, yes, but there are huge controls, at least in this country, on how those chemicals are handled and what is done with that waste. It's not just thrown into the ocean or into the ground. I think the bigger issue is all the pieces of hardware, all the computers and all the phones and all the plastics and everything, and how that is handled out in the world is a major issue.
Is this something that concerns you, Sophie, as someone who's worked with one of the most powerful producers in this technology? Because it has the ability to have an impact on all our smart devices. But there is a question of what happens when we want to upgrade and chuck those devices away.
Smartphones are a peculiar thing. There's a fair load of silicon in them, but there's an awful lot of other stuff in there that's very difficult to recycle because it's in small amounts, but very rare. Trace elements in there, there's gold in there, there are all sorts of things to make things like the touch screen work, the little buzz that the device gives when you touch it, the haptics. There are very powerful electromagnets in there built of rare earth elements. And we're running out of some of these things, or rather they're getting harder to find in the world. Some of the trace elements in a smartphone are byproducts of other types of mining, and we're not doing so much of that mining, so they've got rarer again. But the smartphones are only a small part of the picture because they're not most of the devices. So most of the transistors that have been built in the world, most of the ARM microprocessors or other microprocessors, they're still in use because they're in things. They're not in computers or phones. They're in equipment that's deployed, and that equipment's designed to run for quite a long time. Only gets replaced very rarely, and it's stacked full of firepath microprocessors.
This is the size of a computer today, as powerful as the biggest of only a few years ago, but 1,000 times cheaper. What makes it possible is this. It's called a microprocessor. Electric pulses being directed by switches. By sending the pulses along different channels, a chip can be made to do anything from arithmetic to reading a book. Such chips will totally revolutionize our way of life. They are the reason why Japan is abandoning its shipbuilding and why our children will grow up without jobs to go to.
Gloomy predictions for the future there from the BBC archive in 1978. There is another issue which gets raised a lot in the question of how our world has changed with silicon chip technology, and that's what it's doing to our everyday lives and the way it's changing the way we all operate. There are a lot of people who worry that there won't be enough jobs for people, or the loss of privacy that we are in danger of confronting online, the loss of control over personal data, that perhaps this is becoming a technology which for 40 years has seemed as though it liberated us, that that's not going to be the case in the future. Vin?
I am concerned because I think we are in the second half of the chessboard on Moore's law, and as humans, we are not capable of comprehending other than linear changes. These are exponential changes in the second half of chessboard, means things are going so fast that even we cannot perceive how fast they are. And we see day to day this driverless cars coming on board in next decade, and 3 million truck drivers losing their jobs, things of that nature, with financial computing happening and banks tellers losing their jobs. I think this is all going to compound rapidly, I'm afraid, to a point that we as a society are not heeding enough to make sure we are prepared to deal with what I call jobless economy that's going to be there, but it's going to be significant more in a decade or two.
We have in this programme been surveying the most extraordinary changes in the last 40 or 50 years, and the four of you have been very closely involved in this. And I just finally want to go around the table and ask each of you, if you look back to where you started in this industry and where we've got you now, could you ever have imagined we would have got this far, this fast? Wendy, you were responsible along with Sir Tim Berners-Lee for developing an early version of the World Wide Web, and now we're looking at where the world has taken us since that happened. Would you have ever thought it would go this fast?
I was involved in developing multimedia systems in the 80s, and it was the idea of putting video on computers was completely science fiction. And to be able to think about walking down the street, looking at video on a mobile phone, it's just mind-blowing that that's happened within the space of about 25 years. Just wouldn't have thought that would be possible.
And what about you, Sophie, the journey that you've taken and the world has taken since those early personal computers which you were involved in?
I had goals. So very early on at Acorn, we'd built the Acorn Atom, and I imagined that we'd be able to build a computer capable of displaying an animated merry-go-round from a fun fair. And one of the early demonstrations of the power of the Acorn Atom was to show a picture of that was going round, but not in the way we understand 3D graphics now. I've been quite pleased with what's happened over the time. I have a slight reflection on where I think transistors will go as well, which is kind of fun. So a research department has built a 1 nanometer transistor. They can't mass produce it at the moment, so it's useless for producing integrated circuits. But it's tiny. It's a 1 nanometer transistor, and it's built of molybdenum disulfide and carbon nanotubes. So I imagine that in the future we'll have to change the name of Silicon Valley to molybdenum disulfide Valley.
Well, who knows if we'll all be alive to see that. Vin, you're known as the father of the Pentium chip for one of your inventions, the highly successful Pentium processor. Could you have imagined this would have changed so much?
Not by a stretch of a mile. No, absolutely not. I'm amazed how far we have gotten, how quickly, even though I was right in the middle of it myself, doing it and making it happen. It's still very surprising.
David, a final thought from you.
I have done dozens of oral histories of pioneers in the computer business, particularly Silicon Valley, but outside as well. And one question I quite often ask these people is, did you have any sense of what you were doing and how it would change the world? And usually the answer is, we had no idea. We were just in the right place at the right time. We put the pieces together. We did our job. It's only when we look back that we can appreciate what we've accomplished. There was very little sense as to where it would be taking us in the future. Some more wonders to come. I can't project what they are.
Well, I'm afraid this is where we're going to have to leave this discussion. It's been absolutely fascinating. Thanks to the four of you very much. Vinod Dham, Dame Wendy Hall, Sophie Wilson and David Law. Don't forget, if you're listening, there are lots of other forum topics to download as free podcasts from our website. Just head to bbcworldservice.com/forum. And I'll be back with another programme next week to discuss the life of the exotic dancer, femme fatale and legendary spy, Mata Hari. Till then, have a good week.
If you've enjoyed this BBC podcast, why not try others, such as In Our Time, where Melvin Bragg discusses the history of ideas. To find out more, visit bbc.com/podcast.